How's everybody doing? It's Wednesday, so that means the next class period there's a test. Now the question's been asked, do we need to come to class? And the answer is no. Okay, the test is electronic. It will start at 1, that's when it's available to you. But as soon as you open it, you are limited to 2 hours to finish it. Okay, so it will be open from 1 p.m. tomorrow, or not tomorrow, but Friday to 1 p.m. on Saturday. So you could wait till Saturday morning to take it if you would like. That's your choice. Okay? So if you're more of a morning person, take it in the morning. If you're more of an evening person, take it in the evening. But you are limited to 2 hours on the taking of it. It is all multiple choice. It is 25 questions. Okay? And so work through it efficiently if you can. There is maybe more math problems, but most of them are very straightforward, right, to do. So I tried to make them very clear. There's some balancing equations, identifying types of equations, those types of things, okay? You may use your book and you may use your notes, but I'm asking your honor to not use any outside resources, okay? Is that fair? All right, so I'm going to hold you to your honor as best I can, just by getting it from you, okay? So the only person you'd be cheating is yourself, right? When you get to the standardized test, the MCAT, the GRE, or whatever it is you need to take to move on to the next level, and you haven't learned how to do these types of things, then you'll fail there, right? Does that make sense? So you're only cheating yourself when you do that, okay? So I'll put it that way. Yeah, I got a couple lab videos filmed for the next lab. I'm actually going to do it in a series of 2, so there'll be 2 lab quizzes for the next lab is the cyanide ion, and it will last 2 weeks. The first week we're going to synthesize, kind of like we did with esters, and then the second week we're going to do some paper or thin layer chromatography and a titration to determine purity. And so we're going to learn a new technique called chromatography. Cool? So that's the first one of those is available, and it'll be due next Tuesday / Thursday, depending on when you have lab. I'll try to get it done before you come to lab, please. There's helpful hints and tips on those. And so be aware of that. I added a seats to the general chemistry 2. I also added a lab section. And I have a favor to ask of someone who has Thursday morning, or 2 of you, more than 1. If you have Thursday morning available, that you might switch to that lab, okay? There's a few people that are waitlisted for the Tuesday labs, and so that we get a few more students in there to balance out the numbers in all 3 lab sections. And that those people who, because of schedule conflicts, might have an opportunity to take both courses they need. So if you have a favorite lab partner, you might get together with them and figure out when you guys can do that together or something along that line, right? So just throwing that out there. Cool? Any questions on that? No. Anything else that you guys can think of? So quiet. Presidential election? We don't have a president yet. You guys know that, right? You know, and it's within a 1 percentage point in about 3 states that are going to decide it. So it's going to be right down to the wire. It may take a week to find out, which is kind of amazing, right? The Republicans held the Senate, they believe. Democrats actually lost a few seats in the House, so we'll have the majority. So it'll be a split Congress once again. But you guys know that we make more money in like our stock market when it's actually a non-divided House, no matter which party it is. So because they work together to accomplish tasks and the nation's happier instead of fighting all the time. let's get rid of this fighting. Let's be united, no matter who wins. One government, one people. And it's for us, it's not for one party or the other, it's for all people, right? Or actually there's more than two parties, I should say it that way. Right? And then there's a group called independents, you guys ever heard of those? Yeah. They deserve a voice. So anyway, throw it out there. Since we're in the middle of it, but it's been fun. How many people stayed up way late last night? That was me. Yeah, I'm kind of dragging today. How about you guys? Yeah. So anyway, well, let's do a little bit, a couple more types of problems, okay? These are summations. So summations are nice. There's a little multiplication involved, but to get to the right place. But I showed this equation last time, and this is showing the delta H of the reaction, right? What did the little zero mean? What did the little zero, the naught? Standard state, right? Standard state. So these are going to come from tables, right? In fact, the table that you're going to get the values to calculate with is Appendix J in your textbook, or when you're doing them on sapling, then they actually have a clickable table, right? I'm pretty sure that's right. I remember last time I did one. Cool. All right. And so in this, it's the sum of the moles times the delta H of formation, and that's what you find in the table, okay, the delta H of formation. And this is of the products minus the sum of the moles times the delta H of formation for the reactants, okay? So if we look at the next page, I have one of those set up for us to do, and this is the reaction, okay? So we want to know the heat that will be produced from this reaction. You guys with me? Now, we're going to do it using the mole ratios that are given in the equation. Now, we could, as long as we have the right ratio of all of those, we can do it for any amounts. Okay, so just be aware of that. All right, we're going to do it for the whole number balance in this case. So what we need is, we need for each of the compounds that are in this, right? The benzene C6H6 for O2, for CO2, and for H2O, we need the delta H of formation. I'll put that up here. Right? Standard state. And so we would turn to Appendix J and we would scroll down until we found liquid benzene. Right? You guys with me? Notice this. The state that it's in is very important in this, because there'll be a gas one, there'll be a liquid one, and a solid one possibly, right? Now realize our table in the textbook is limited. So when I did that, then from Appendix J, I found these values when I looked them up. Okay, you guys with me? So I went down through there, found the compounds, and I found the delta H of formation for each of those. And I found the first one to be plus 49 kilojoules per mole, and I found the O2 to be 0, right, because it's in its elemental form, and kilojoules per mole. And the CO2 in the gas phase is negative 393.5 kilojoules per mole, and the last one is negative 241.8. That's water when it's a gas, kilojoules per mole. So there's a different value when it's a liquid. Okay, you guys with me? Because there's a phase change that has to occur, so the energy, the internal energy changes during the phase change. So now what do I do with those? I literally plug them into that equation I showed on the previous page. Okay, so what's my first product? CO2. So I would take the CO2 value, negative 300 and negative 393.5 kilojoules per mole, and I would multiply that times the number of moles from the balanced reaction. And what's the number of moles up there? 12. So 12 moles times the 393. And so that's the term for CO2, right? So that's my first product. And then I would add that to my second product. And what's my second product? It's water, right? And how many moles of water? 6 moles of water times negative 241.8. And all right, so this is for the H2O. All right, and I'm going to put a bigger set of parentheses around that, right? And I'm going to just indicate that this is the products, right? You guys with me? So what's the next step?
Subtract it from the reactants.
Subtract the reactants from that's products minus reactants. And so then we would set up the reactants. And so that's 2 moles times C6H. I'm going to scribble or wipe out times plus 49. I'm going to leave that sign on there just so I know. Okay, maybe I shouldn't. Might get confusing. C6H6 and then plus 12 mole. Is that right? No, 15 moles. I'm having trouble connecting up there. 15 moles of O2 times, what am I multiplying the O2 times? 0. And that's O2. And this equals the delta H of reaction. So we took the 2 delta H's of formation and we combined those to find the delta H of reaction. Okay? So at this point, you just do your addition and subtraction. So products minus reactants. It's fairly straightforward, isn't it? You know, just plug in the values that you find in the table and calculate to the end. Okay, so I got 6.2, right? 6.2 kilojoules, and the sign is negative. What does that mean for the reaction? It's exothermic. That's exactly right. Heat is produced, right? So we're doing a combustion reaction, and that makes sense, doesn't it? Okay. So negative 6.2 times 10 to the 3rd kilojoules. Yep.
Is there a reason why you switched to scientific notation?
I just, when I did that problem, I was in a scientific notation mood, and right, my calculator gave me that answer in scientific notation, the one I was using that day. Yeah, but we wander back and forth between those worlds fairly easily. Yeah. All right, questions on that? No. So on the next page, I showed this to you before we left last time, and this is the exact problem. Well, just a different, instead of having C6H6, right, it has C8H18. You guys see that? And that's actually the value, not the delta H of reaction, which we just calculated there, right? They give you the delta H for the reaction. Sapley does, okay? It's right up there in the top. You guys see that? Yeah, so they give you the final answer, right? And then they ask you to set up this equation, right? And they want you to find the delta H of formation for the hydrocarbon. You guys with me? And so you set it up exactly the same, where you have moles of product, so you would have 8 times the CO2 value, which is negative 393.5. Now be careful, these are textbook values, and the ones on sampling may be slightly different. Okay, the thermodynamic values vary depending on the literature. Okay, so and so that would be the CO2, and then plus 9H2O, right? And then minus 1 mole of the C8H18 times X, right? And plus the 25 halves times 0. Cool? And then solve for X. You guys catch that? Okay. I'm going to leave it there since we just worked one. And if we need to, I'll set this up next week if you guys still are struggling with it. Okay? Cool? All right. One more set of rules, and then we're going to look at what's called Hess's Law. Okay? And so these are things we've already been working on. And I have mentioned all three, I believe. Right? But the first one is that the magnitude of delta H is directly proportional to the amount of reactant or product. If I have 1 gallon of gas, I can go half as far as when I have 2 gallons of gas. You guys with me? Does that make sense? So the heat related to that, it would be the amount that would be proportional. Okay? So be aware of that. Okay, that's the first rule. The second rule I know we've discussed is the delta H for reaction is equal in magnitude but opposite in sign for the reverse process. Right? You guys with me? It's equal in magnitude but opposite in sign. So if I look at a reaction backwards, right, then it would have the same magnitude of delta H, right? If it's exothermic, then to go the other direction, it would be endothermic. Okay? All right? And this is some examples of just a process freezing, right? And cooling. To go from liquid to solid, I have to remove heat, right? If I have 1 mole of that, it would be 333 joules, right? And if I flip that and go the other direction, right? So I would have to remove 333 to freeze it. I would have to add 333 joules to melt it. You guys with me? Okay. So you guys got that one. All right, we've worked on that. This one I know I've mentioned, or I believe that I have, and it's that when I have a multi-step process, right? When I have a multi-step process, I can find the overall enthalpy for the process by summing the steps. Okay? And I've mentioned that in some of the graphs that we've looked at and those types of things. That enthalpy is a state function, so we can get to it from multiple ways. Okay? It's describing where we're at, not how we got there. You guys with me? Okay. So the way we do Hess's law is shown there. The delta H for the overall process is the 1 plus 2 plus 3, or however many steps it is. Okay? So I'm going to give an example here, and this is a reaction. Okay? And so this reaction is methane plus oxygen yields CO2 plus water. Okay? Methane plus, so this is another combustion reaction, right? But if I look at the reaction itself, I can get there with 2 reactions, okay, or 3 or 4 or however it may be. And so if I don't have the delta H for a reaction for the top one, but I have it for these other reactions, then I can sum the reactions together to find the final delta H value, okay, or the total delta H. And now, I want you to look at this for just a second. And so these are the steps that we would have. And so the methane going to carbon plus hydrogen, right? And then oxygen on both sides there. And that's an interesting one. And then the carbon plus oxygen yields CO2. And then H2 plus O2 yields H2O. Okay, you guys with me? So now, what I want you to do is the same thing we've done before, where when we add things together, right, you cancel like things on both sides of the arrow. You with me? So if I'm looking up here, then I have carbon on the right-hand side of that first reaction. Where is it on the next reaction? 2 down. It's left of the arrow. Do you guys see that? Here, let me get, So if I'm looking here, I've got carbon on the right side of the arrow and carbon on the left-hand side of the arrow. Right? Now what I want you to notice is there carbon anywhere in the overall reaction. Not by itself. Okay? Not as an independent species. So I put an X through that and I put an X through that. Okay? It goes away. And then I look at H2. Is there H2 anywhere up here? There's not, is there? So I'm expecting to find H2 on the other side of the arrow in one of the reactions I'm adding together. You guys with me? And so when I do that, then I cross out my 2 H2s. Now I've got the oxygen, right? And now there's 2 on this side, and on this 4 total on this side of the arrow, and 2 on the right-hand side of the arrow. So that means that 2 of those are going to go away. Okay? Now, so I cancel those, I leave those 2, and now CO2 is my product. I don't find CO2 over here anywhere, and H2O is my other product. So when I do all that cancellation, then I end up in that with the reaction at the top of the page. You guys see that? And so then if I take the delta H's from each one of those reactions, okay, the delta H of reaction, then what I find is that the delta H for this reaction can be calculated from those 4 steps. Okay? Now, I did this one without numbers. We're going to do the next one with numbers. Okay? Now, there's something else you should note is that when you look at that overall reaction and then you start looking at the steps and you find that you have the same terms on the same side of the arrow, what can you do with the reaction? Can you flip it over? But when you flip it over, what happens to the sign of the delta H? It becomes the opposite sign. You guys with me? So you guys kind of catching that? That's why those other 2 rules are important and why we started teaching those. So here's our reaction, for example 2. We're going to plug in some numbers, use these equations to calculate the molar enthalpy change, which produces hydrogen gas. So I'm going to give you 2 equations. And so there's your 2 equations that you're going to add together to make this reaction occur up here. So I've got H2O on the left, right? Do I have H2O in either of these reactions down here on the left? No, what does that suggest you're going to have to do? You're going to have to flip that reaction to get it on the same side as the desired endpoint. Okay, you guys with me? So I'm starting up here. So I've got carbon plus 1/2 H2O, or excuse me, 1/2 O2. My bad. O2 yields CO2.
Shouldn't it just be CO?
Oh, CO. My bad. I read that wrong. All right. I apologize. Yes, I just added that just because it's normally CO2 for me, right? It was at least in lab last week or week before last. And then the second reaction, now note the carbon is on the left-hand side in both the step and in the main reaction, right? You guys with me? So I'm going to leave this reaction the same, but I'm going to take the second reaction and make it H2O gas, right? Going to H2 plus 1/2 O2. Okay, cool. Now when I did that, this is still negative 110 kilojoules, and that should be mole. And then this one is negative 241, so we're going to change the sign to positive 241.8. Okay? So now we're going to add these together. All right? And I'll put a plus sign right there. Okay? And you can actually, I add down in both cases, right? So just to let you know that that's what I look at. But if I'm looking, carbon stays, right? The O2's canceled, okay? And so we have carbon plus H2O. And that's going to yield CO plus H2. And this is a water reaction that occurs in reducing systems, for example, in gasification. Okay, so to produce a couple combustible gases, syn fuel, and those types of things. Okay, cool. All right. So, what's the delta H of reaction for this based on Hess's law?
131.3.
What is it?
131.3.
131.3 kilojoules per mole. And so that's the way you do it. It's not too bad, is it? All right. So not too bad. You guys want another try? The next one's a little more complex. There's more steps, okay? And so, and you notice something nice about this one. You guys know the mole ratios were all 1 to 1 to 1, right? Not so in the next one, okay? So in this one, then you're going to have to work on mole ratios to get there too, okay? So we've got three reactions that we're going to, three-step reactions to get there. And so the delta H of reaction is going to be found by adding together delta H1, delta H2, and delta H3. Okay? So start with reaction 1. Is the C4H10 on the left or the right of the final reaction? It's on the right. So what are you going to have to do with that? You're going to have to flip it over. So start by flipping that one. Start by flipping the first one. So, anything else going on right there? You got that one flipped. So we've looked at reaction 1, right? And so we turn that over. And so now we've got that as positive on the kilojoules per mole. Okay? So we reverse the sign. And so anyway, how about the second reaction? What have we got going there? Is the carbon on the left or on the right-hand side in the final reaction? It's on the left-hand side, so we're going to be probably leaving this one the same direction right now, right? So go ahead and leave it the same direction and write it in. And then we're going to make a change. What change do you see needs to be made?
It needs to be 4 carbons.
It needs to be 4 carbons because there's 4 carbons in the final reaction. So how do you get it to 4 carbons? Multiply everything by 4. You guys with me? Multiply everything by 4. And so it's going to be 4 carbons plus 4 oxygens yields 4 CO2. So what did I forget to multiply times 4?
Your delta H.
The energy out there, right? The delta H. And so don't forget the way we're doing this with Hess's law, you have to count for the change. And so it's going to be 4 times that value. Okay? So 4 times the delta H. And so don't forget to do that. Okay? Don't forget to do that. So how about the next reaction? What about it? Is there H2 on the left or on the right? It's on the left, so we leave that one in the same direction, right? So is there molar changes that are going to occur here? Yeah. So I multiply everything times 5, right? You guys let me do that? Somebody can scream? You guys okay? Just checking. So there's our 3 reactions. We've rearranged those to where we need them. Okay, we've rearranged those to where we need them. And so then we're going to sum the delta H's, and we're going to sum these and make sure that we get to the right place in terms of the reaction. I'll let you guys do that. I'll let you do your cancellations and try to do those without me. Bless you.
Thank you.
We've got delta H of reaction is negative 125.6. Yeah. Yes, sir. We got it, yeah. Questions on that? This is a setup, learning how to set it up, right? So what happens when we reverse a reaction?
The sign.
Changes the sign, same magnitude, right? If we multiply something by a factor of whatever that value may be, then we would multiply the energy in this process by the 5 times the amount of fuel, for example, or 5 times the amount of oxidant, and so that energy would have to be multiplied by that, right? Like adding 5 more gallons of fuel. Okay, cool? Yeah. All right. Those are the Hess's law problems. I want to connect that a little bit to biochemistry, just to tie it together. And so Hess's law is path independent, right? So if we know the number of calories that we can get from food in a bomb calorimeter, is that the same number of calories that we can get from food when we put it in our digestive system? You guys catch that? Yeah, so we can measure that experimentally in the laboratory and know what we're getting when we eat it. That's how that's done. It's kind of cool, huh? So a nice connection. And so protein plus oxygen yields byproducts, carbohydrates plus oxygen. It's the same as a reaction like this. And so we can know the amount of energy that we're going to get from that. Okay, in fact, we can do an energy balance for this. All right, calorimetry is the same reactions, just different pathways. So kind of wanted to connect those things. All right. Now wait a minute. Why doesn't it get as hot in our stomach? Instead of burning it, we cut it up with enzymes, don't we? Right. So we lower the amount of energy that's needed to get it started, and then the rate at which it comes off. And so but do we heat some? Do our bodies stay warm? Yep. So just realize that we use a little bit of that. All right. There's one other thing. This is actually in a later chapter. Okay. I just flipped this. If you had printed the notes, I moved this in position because I wanted to make sure that I got those other calculations done before I did this. But there's another way to actually calculate or estimate the delta H of a reaction. Okay? And it's through bond energy. Now, this in my mind is the least accurate, but it's a good place to start if you don't have the standard state values for that particular compound. Okay? And so the way you do that is that you know, number one, bond breaking is endothermic. We have to put in energy. You guys get that, right? To pull 2 magnets apart, then it takes energy to do that, right? And then when we put those magnets in the right proximity with each other and they come back together, what happens? Do they stick? Will they pull themselves to each other? Yeah. And so realize that in that, I kind of think of that as when we're doing chemistry and we're making and breaking bonds, and things are attracted to each other, and well, the things that are most attracted to each other like to end up together, okay? And those that aren't as much like each other don't. And so we go to usually a lower energy state in that case. All right, so chemical reactions usually involve both bond breaking and then bond making, right? And so in your book, and I can't remember, the bonds broken to get to the delta H of reaction, the energy of all the bonds broken minus the energy of all the bonds formed is a nice way to estimate that. And so you have to know how much energy it takes to break bonds. And so this is showing an example of bonds where to break the hydrogen, the H and H, to pull those two apart, right? And to take the Cl2, the Cl and Cl, and pull those apart, we have to put in 678 kilojoules per mole, okay? And so, but when we're doing that, then each one of those has one bond to break, and so each of those requires different amounts of energy, and those are tabled, right? And then when we reform bonds, right, when I have a hydrogen and a Cl that come together, then that's exothermic and energy is released, okay? And so when they come together, then you notice the sign has changed over here to negative. And so when they come together and make HCl, right, then we have those two new bonds, two relationships that come together to make that happen. And the difference between those is negative 184 kilojoules per mole. And so we gain that in that process, okay? So we gain that in that process. Now, in other words, this is better shown. That D should have been a delta on that previous page, but the delta H of the bond's broken minus the delta H of the bond's formed. And the bond energies that you do this with are actually in chapter 8. The reason it's in chapter 8 is because we haven't done bonds yet, right? And so next chapter, we'll begin that adventure into the quantum world and bonding and those types of things. And so that's why this is in chapter 8. But I think that it should be connected to what we're doing right now, okay? Because this is another way to do what we're doing right now. Does that make sense? And so I'm introducing it to you here and saying that when chapter 8 gets here, then we'll do these calculations, and I'm just going to show you this one very quickly. And so if I have CH4, how many carbon-hydrogen bonds are in CH4? How many carbon-hydrogen bonds are in CH4? There's 4. It's that, you guys can do that, right? In fact, if I draw it over here, one, two, three, 4, right? You guys with me? So there's 4 CH bonds, and for each of those, right, it takes 416 kilojoules per mole to break those. Okay, so I would multiply 4 moles, right, CH bonds. There's 4 moles per 1 CH4, and I would multiply those together, right? And so then I have oxygen bonds, right? They're double bonds. And so when I look up in my table for an oxygen double bond, then I have 2 moles of, now I have to be careful because there's 2 moles in the reaction. You guys see that? I have to consider that stoichiometry too, in addition, right, to how many double bonds are there in one oxygen molecule? There's 1 double bond. You guys with me? So there's 2 moles of O2, so I have to consider that 2 double bond oxygen-oxygen bonds are broken in this case, right? So you have to do that count. And so that's 2 times 498 kilojoules per mole, okay? And so this is the reactants, right? And then to get the bonds, I should say, the bonds broken, that's the term I use up there, so, all right. And then the new bonds that are formed, right, the new bonds that are formed, there are 1 CO2 molecules, but how many, well, if we have to draw the structure, right, of CO2, and maybe I should have done oxygen, right? And then what's the last one? H2O, right? And so that's the structure there. And so to do the last, or the bonds formed, then the CO2 is 2 moles of the carbon double bond O times 803 kilojoules per mole. And then we're going to add that to well, if I'm looking at water and I look up there, how many moles of water in the reaction? 2 moles. And then how many moles of bond in the moles of bonds in the compound? 2. So that's 4. You guys get that? So 4 times, and 4 moles of oxygen-hydrogen bonds, and those are 467 kilojoules per mole. And this is formed. And so then I take the bonds broken minus bonds formed, and end up with negative 814 kilojoules per mole. Okay, that's the delta H of reaction. So that's another method to do what we did on this problem, okay, where we looked at the delta H of reaction using the standard enthalpy of formation. When you don't have those values in a table, or you don't have stepwise reactions like in Hess's law, then you can estimate it with the bonds. Does that make sense? Yeah. And so I feel like that should be shown right there. That's all the material that I have for chapter 6. Okay. That I'm going to go over before the test. And so have a wonderful day. And is anybody going to come to the classroom to take the test? Okay, I didn't think so, but I just thought I would check. So if you have issues, please email me, okay, text me or whatever that